So now this time, to solve an equation like this one, we've got 2 times the sine of x times the cosine of x is equal to square root of 3 times the sine of x. We do have to remember that there is a certain principle at work right here. Namely that we have the kind of equation in which it would not be appropriate to divide both sides by sine of x, right? If you remember, when we were dealing with similar kinds of equations in algebra, what we try to do is if we had a situation that might involve factoring, we should set the equation equal to 0, factor out common factors, and then determine what values of x make that equation true. Well, the same thing is true here. So, starting with 2 times the sine of x times the cosine of x, and setting that equal to the square root of 3 times the sine of x, the easiest way to handle this situation is to subtract square root of 3 sine of x from both sides of the equation. So I'm going to do that this way here. I'll just go ahead and erase my equal sign and replace it, because I'm going to be subtracting that quantity now, and I set it equal to 0. Well, that's a really useful thing, right? Because we know then that what we can do is that in order to solve this equation, we're going to get a factorization. So we're going to factor out sine of x. We want to simplify these expressions because factored forms are often much easier to deal with than non-factored forms. So we've got sine of x times 2 times the cosine of x. Cosine. X is a funny looking cosine. We'll try that again here. Cosine of x minus the square root of 3 equals 0. Okay, so what do? Well, whenever we have two factors multiplied by one another and set equal to 0, that means we're going to have two kinds of answers. One will be the kind of answer where when we take the sine of x and set it equal to 0, the value of x makes that equation true. The other one is going to be the kind of equation where I have 2 times the cosine of x minus the square root of 3 equal to 0. All right, so let's go to what we know about sine of x and where it's equal to 0. For one thing, we know that at x equals 0, that's true. We can take the arcsine of 0 and we get 0. Right? In other words, sine is the kind of function whose sine of 0 is 0. So x equals 0 is one solution. But on the interval from 0 to 2 pi, are there any others? Well, let's think about this. If we were to go to a unit circle, it looks like this is a quadrantial angle. So we ask, well, are there any other quadrantial angle positions for which we have a 0 for sine? We know that on the horizontal axis, if this were a unit circle, our y value should be 0, because that corresponds with the sine or cosine. So we go back over here, and our y value is again 0, and this time it's at the position pi. And so we say, well, that means that x equals pi must be one other of these solutions. Now, if you wanted to, you can think about this 0 as being a reference angle, and pi minus 0, which is equal to itself, is just another form of that solution. So we've done well. So there it is. Okay, so how about this one? 2 times the cosine of x minus square root of 3 equals 0. Well, now we can isolate cosine of x right here by adding radical 3 to both sides, so that 2 times the cosine of x is equal to the square root of 3, and dividing both sides by 2 gives us cosine of x is equal to positive radical 3 over 2. Now, this is a first quadrant angle. I know that if I were to take the arc cosine, or the inverse cosine, of radical 3 over 2, it's going to be the kind of value associated with the angle pi over 6. Right? So recognizing that pi over 6 is a first quadrant angle, our quadrant 1 position for which this is true is the angle pi over 6. But are there any others on the interval from 0 to 2 pi for which this is true? Well, our little saying, all students take calculus, means that in the fourth quadrant, we're also going to find the kind of angle that would have a cosine equal to positive radical 3 over 2. So we do that. In this case, our quadrant 4 angle can be found by taking 2 pi and subtracting the reference angle of pi over 6. And so our other value here is going to be x equals 5 pi over 6. Sorry, not 5 pi over 6. Not pi minus pi over 6. It's 2 pi minus pi over 6, right? That's 12 pi over 6, 11 pi over 6 when we subtract pi over 6 away from that. All right. And so our solution set is going to be the set 0, pi over 6, putting everything in order, pi, and 11 pi over 6. And the nice thing about this is that you can check this solution by substitution, going to the original equation. And just to show you why it must be true, let's just take pi over 6 as an example right here. If we were to put in pi over 6 and check that, I'll do that over here in green, we know that 2 times the sine of pi over 6 times the cosine of pi over 6 should give us the same thing as the square root of 3 times the sine of pi over 6. And the sine of pi over 6, as we stated before, is equal to 1/2 in some previous examples. Cosine of pi over 6 is square root of 3 over 2. And for radical 3 times the sine of pi over 6, we're taking radical 3 times 1/2. Well, 2 times 1/2 on the left-hand side just gives us 1, so we get square root of 3 over 2. And square root of 3 times 1/2, that's square root of 3 over 1 times 1/2 is equal to square root of 3 over 2. So sure enough, that verifies our equation. And so we're done.